A model can stay deployed while its inputs quietly change. You'll detect data drift in Python with pandas, SciPy, and evidently, before silent distribution shift turns into accuracy decay. This is the pattern you'll be able to implement by the end, which profiles a baseline and checks new data for drift against a threshold. I'm Professor Pi, teaching AI foundations with simple Python. Models assume the future looks like the past. That is the simple failure mode. In production, customer behavior, sensor calibration, or seasonality can alter the input distribution. When inputs shift, model accuracy can drop without any code breaking. Detecting that shift early lets you schedule retraining, trigger alerts, or roll back data collection changes before users notice poor predictions. For many classifiers or regressors, catching drift can preserve tens of % of accuracy loss and avoid costly manual investigation. At the heart, drift detection compares a stable baseline window to a recent window and asks if those distributions differ enough to matter. Think of it like comparing two histograms. If they overlap a lot, no alarm. If they separate, you get a quantitative signal. Strengths are that this is quick and interpretable. Weaknesses are that tiny sample sizes muddy the signal, and that some changes matter more than others for downstream accuracy. We will build a compact, repeatable pipeline. It creates a reference snapshot, observes a fresh batch, runs simple tests per feature, and summarizes whether the dataset deserves retraining. The code uses pandas for tables, SciPy for a classic distribution test, a hand-rolled population stability index for magnitude, and evidently for a one-button report. Nothing exotic. This is a practical pattern you can slot into a monitoring loop. Now we prepare a tiny baseline and a slightly shifted current batch to make the ideas concrete. This snippet builds small reference and current datasets in pandas to make a concrete drift example. The variable ref holds 3 columns with simple, readable values, so it is easy to see how the data looks. The variable ter copies ref, then nudges the price column upward by a few units, adds 1 year to age, and makes city skew more towards C. The transformation makes price and city distributions differ in intuitive ways while keeping the data compact. Finally, the code computes mean shift by subtracting the reference price mean from the current price mean. The printed mean shift shows how much the central tendency of price moved. Next, we run a formal statistical test to see if the price change is unlikely to be random. This example runs a Kolmogorov Smirnov test with SciPy to check whether price changed in distribution. The function ks2samp compares the empirical cumulative distributions of ref price and cur price and returns a distance statistic and a p-value. The variable stat captures the ks distance, which measures the largest vertical gap between the two cumulative curves. The variable p quantifies the probability of seeing such a gap by chance under no drift. The variable isDrift flags statistically significant change at the 0.05 level. If you tighten alpha to 0.01, fewer changes will be flagged. Loosen it, and more will trigger. The printed values indicate if price drift is statistically credible. Now we extend that idea to multiple numeric features, so we can find which one moved the most. This code compares multiple columns by their Kolmogorov-Smirnov distance and picks the most shifted feature. The list calls selects the numeric columns to evaluate side by side. The list comprehension computes ks2samp for each column pair from ref and cur, collecting tuples of the column name and its ks statistic. The variable stats therefore holds an interpretable score per feature that grows as the distributions diverge. The function max then selects the tuple with the largest distance, naming the top drifting feature in top. You can expand cols to include any additional numeric fields. The printed result identifies where drift is most pronounced. Next, we add a complementary magnitude measure that is common in credit and marketing monitoring. This snippet estimates the population stability index for price to quantify shift magnitude. It first finds the combined min and max across ref and cur to create shared equal width edges. The variables RB and CB bin each dataset with pd.cut, so both distributions are counted over identical intervals. Next, R and C compute normalized frequencies per bin and clip tiny values to avoid division by zero and log issues. Finally, the variable psi sums C-R times the log of their ratio, yielding a single drift score. Increasing the number of bins makes PSI more sensitive to local shape changes. Fewer bins smooth small bucks. The printed PSI summarizes how much price moved overall. Finally, we show how a ready library can produce an audit-ready verdict across all columns. This code uses evidently to produce a ready-to-use drift summary across columns. The object report wires in data drift preset, which bundles column-wise statistical tests and an overall dataset decision. The method run executes the preset on ref as the reference window and cur as the current window. The dictionary from asdict provides structured results. The variable d reads the overall dataset drift boolean and the number of drifted columns. This quickly turns per-feature signals into a concise, auditable decision. If you expand your data frame, evidently scales the same way without extra code. The printed fields tell you how many columns drifted and whether the dataset is flagged. In a real project, you would run these checks on rolling windows or streaming batches and log the scores to a time series. You would combine KS flags, PSI magnitude, and evidently decisions into a single alert rule. Keep the same core pattern and scale the windows as data volume grows. Recap what it is: a practical pipeline that profiles a baseline, tests per feature, quantifies magnitude, and summarizes dataset drift. When to use it: anytime you deploy models and need an early warning before accuracy drops. One caveat: small sample sizes can make statistics unreliable, so interpret flags with context. Next step: tune the PSI bin count and the KS significance level to hit the sensitivity that matches your business tolerance for false alarms versus missed drift. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.